Hello and welcome to McLean 360. So in this video, I want to explain to you free damp vibration. Okay, so when we say a free damp vibration system, I have a spring, I have a mass, and then I have a damper. As a matter of fact, the damp is actually coming from the fact that I have a damper present. And that is it. If I have a free system, what this means is that there is no external force acting on the body apart from the body's own forces. Okay. Now, if that is the case, let's look at how to come up with the solution. But then, wait, I have objectives which I want to set with you so that by the end of the video, we will achieve the three objectives together. The first objective I want to achieve with you is the equation, the free body diagram, free body diagram, free body diagram. Okay. The second objective is the equation of motion, equation of motion. And then the third objective is the solution or the response. So the solution or the response. Okay, so now that is it for you. How can I be able to achieve these goals? Let's start from the first objective, which is the free body diagram. So let's draw the free body diagram together. So I have a mass right here. Okay, I have a mass M. Now this mass is giving some displacement positive in this direction. What happens is that, I didn't include, I didn't talk about the reactions here. I didn't talk about friction. I didn't talk about the weight because I'm looking at motion in the horizontal direction. And I'm also assuming that the floor is smooth, so there is no friction. Okay. Now, this stiffness here, which is the spring, is actually, and the damper. So the spring and the dampers are restoring forces. So we call them, they create restoring forces. So what this means is that if I try to displace the mass towards this direction, the spring force will try to push it back. And the spring force is given by Kx. Similarly, the damping force will try to push it back, and the damping force is Cx dot. Okay, so that is my free body diagram. Now, from Newton's second law of equation, I have summation of forces positive in the direction of x to be equal to mass times acceleration. Okay, so I have minus ks. So the minus is coming from the fact that it is opposite the positive direction of acceleration. And minus cx dot should be equal to mx dot dot. Is that right? Now over here, I can say that mx dot dot plus so mx dot dot plus cx dot plus kx to be equal to 0. And from here, I can now say that I have gotten an equation. And to be honest with you, this is the equation of motion. Okay, so we've been able to get, in fact, this is the free body diagram, and that is the equation of motion, this one. And this is actually a differential equation. It's a differential equation. Therefore, to be able to solve this, we need to go back to our differential equation class. This equation is actually a second order system. The second order because the highest order it's 2. And then this is actually homogeneous. So homogeneous in the sense that the right hand side is 0. So it's homogeneous. And it's a constant coefficient. So constant coefficients. And finally, this is actually an ordinary differential equation. Ordinary differential equation because I have only one independent variable, and the independent variable I have in the system is actually time. Okay, so if I were to write this in your differential equation class, you would see this as m d squared x dt squared plus t dx dt plus, okay, so c dx dt plus kx should be 0. Now, this is what you will see in your math class. What this means is that to be able to solve for x of t, you want to ask yourself, is there a function? Is there a function which, if I differentiate twice, multiply by some constant, plus the first derivative multiplied by some constant, plus the function itself multiplied by some constant, should be equal to 0? And that is how we want to solve this. And in fact, the solution, the answer is yes. So there is an answer to your question. And what function is that? In fact, that function is the exponential function. And all exponential functions take this form. Why an exponential function? Because the exponential function will decay to 0. All right. So mostly we choose an exponential function. All right. So you are saying that this is the solution to your differential equation. And if this is indeed the solution to your differential equation, then this must satisfy the differential equation. Okay. All right. So at this point, we want to find the first derivative. Now, differentiating an exponential function is the easiest of all of the derivatives. So I have to copy and paste this, then I multiply by the derivative of the power. And if I want to, so the derivative of the power is actually lambda t. If I differentiate with respect to time of lambda t, I get lambda. So I'm going to multiply this. So you have copied and pasted the function, and you have multiplied by the derivative of the exponent, and you are going to get a. So I'm going to get, for the first derivative, I'm going to get a lambda. So I'm going to get a lambda e lambda t. Is that right? And then the second derivative, I'm going to get, so yeah, I'm going to copy and paste again and multiply by the derivative. So sorry, I'm going to copy and paste a lambda e lambda t. If I multiply by the derivative, then I will get a lambda squared e lambda and t. Is that right? Now, after getting this, what I will do is that I will go back. Okay, I will go back. So this is my m, which is my mass, right? This is my mass. Then I'll multiply this by a lambda squared e lambda t. Is that right? Plus c, which is here. Then I'll multiply by the first derivative, which is a lambda e lambda and t, plus k. Then I'll multiply by the function itself, which is a e lambda t, and this is equal to 0. Okay, so some terms are common. Let's bring them out. Which terms are common? Yes, you are right. It is a, and then e, and then lambda and t will come out. Then I have m lambda squared plus c lambda plus k to be 0. Okay, so when I get to this point, I want to ask myself, I have two functions multiplying to get 0. One of them must be 0, or both of them are 0. But you know what? A e lambda t cannot be equal to 0. In fact, if a e lambda t is 0, I need to stop making this video, and we need to stop learning vibration, because the x, which is our vibration, is 0. But our vibration is not 0. So we need to continue. Therefore, a e lambda t cannot be 0. Therefore, m lambda squared plus c lambda plus k must be 0. Okay. Ooh. Now, when you get to this point, you have gotten to something you are familiar with, right? Something you have been doing right away from your elementary school. And this is what we call the quadratic equation. So I've gotten a quadratic equation, which is in terms of lambda. And to find the root of this quadratic equation, I'm going to use what we call the almighty formula. I'm sure you know this formula. So let a quick recap. If I have ax squared plus bx plus c equals 0, then we said that the root is what? X, which is going to be minus b plus or minus the square root of b squared minus 4ac all divided by 2a. This is what you did in your math class so many years ago. Now it is time to apply it here. So if I have this, then my root is going to be lambda, and lambda is going to be minus b. So what is b? The coefficient of x. So this time around, the coefficient of lambda, which is c, plus or minus the square root of b squared. So it's going to be c squared minus 4a. So a is the coefficient of x squared. So a here will be the coefficient of lambda squared, which is m, and I'll multiply by c. Over here, don't be confused. Over here, c is k, which is the constant term. So 4mk, then I'll divide this by 2a, and a is the coefficient of lambda squared, which is m. All right. Now we have been able to get this, but you know what? There is this quantity called c squared minus 4mk. And you know what? The value under a square root sign will depend on this, the answer for this, right? And you know, you were taught from your high school or whatever math class that this is called the discriminant. So this is the discriminant, and this discriminant is actually going to decide the values we will get for the roots. If this discriminant is, so if whatever is under the square root sign is going to be 0, then we are going to get what? Unique roots. If it is greater than 0, we are going to get real and distinct roots. And if it is less than 0, we are going to get complex roots. Is that right? But we are not in the math class. We are in a vibration class. So what we will do here is that we will equate this c minus mk to 0. And by equating c minus mk to 0, we are trying to say that the critical value of c, which we will get, is c critical given by, so if I take the roots, I'm going to be square root of 4mk, and that is what? 2 root of mk. And we call this our critical damping coefficient. So the critical damping coefficient of a system is given by 2 root mk. And what do we mean by critical damping coefficient? We already have a damping coefficient, which is the c. Therefore, we define a parameter for the damping ratio. So we have what we call the damping ratio, or sometimes called the damping rate. So either the damping ratio or the damping rate. And this parameter measures our actual damping. So damping ratio equals actual damping divided by theoretical damping or critical damping. Is that right? And this actual damping is our C, and the critical damping is our CC. Okay. So if that is the case, then we can say that our damping ratio zeta is C divided by 2 root mk. And that we can also say that our damping coefficient C is going to be 2 zeta square root mk. Okay. Let's try to do some gymnastics here. Let's try and do some gymnastics here. So what have we learned so far? So in the previous video I did on this free damp system, we said that omega n squared, which is the natural frequency, is given by k divided by m. And if omega n squared is k over m, then it means that if I multiply, so we want to do a gymnastic here. So we want to say that m multiplied by k is the same as what? M squared multiplied by k over m. Mathematically, this is correct, because if I divide this, I'm going to cancel m by one of the m. And so we are saying that this equation or this statement is valid mathematically. And if that is the case, we know that K over M is omega n squared. Therefore, M multiplied by K is the same as M squared omega n squared. Therefore, if I take the square root of mk, this is the same as taking the square root of m squared omega n squared. Therefore, the square root of mk is the same as m multiplied by omega n. This is very much interesting. So what this means is that instead of writing 2 zeta root mk, I can also write this as c equals what? 2 zeta omega n times m. All right. That is very good. So since I have c equals 2 zeta omega n times m, I'll come back. So you see, I said that lambda was what? Lambda was minus c plus or minus square root c squared minus 4mk divided by 2m. Okay, now I know c. So what is going to, I'm going to put 2 zeta omega n m into it. So this is what we are saying. Lambda is minus c plus or minus root of c squared minus 4mk. We are dividing all of this by 2m. Now, since we know that mk is that, let's do it together. Lambda is going to be minus, c is what? C is now 2 zeta omega n times m, plus or minus 2 zeta omega n times m all squared. Is that right? And then minus 4mk. And we said that mk is the same as what? M omega n. Okay. No, mk is actually m squared omega n squared. But the root, okay, so this is what we are saying. Mk is what? M squared multiplied by k over m. So it's going to be m squared omega n squared. So here is going to be m squared omega n squared. Then I will divide, I'm going to divide the whole of this by 2m. All right. So over here, what I will do is that I have minus 2 zeta omega n times m plus or minus. And then I'll square this. I'll get 4 zeta squared omega n squared m squared minus 4 m squared omega n squared. And I will divide everything here by what? 2m. Okay. Therefore, I can see that my lambda is going to be minus 2 zeta omega n m plus or minus square root. Now 4 is here, 4 is here. Omega n squared is there, omega m squared is there, m squared is also there. So I have 4 here, I have omega n squared, m squared, 4 omega n squared, m squared. So it means I can factorize everything out, then I'll get zeta squared minus 1. Okay. Now, having done this, I'll divide the whole of this again by 2m. Looking at this carefully, I can say that I can actually factorize to 2 zeta omega n m plus or minus, then the root of, so the root of 4 is going to be 2, the root of omega n squared is going to be omega n, and the root of the root of m squared is going to be m. Then I'm going to do square root. So this I'm going to be what? Squared minus 1, and I'll divide through by 2m. Clearly, we can see that this m, so if I factorize again, I'm going to do 2. We'll come here, so I have 2, and then m is here, so 2m, and then I'm going to get, okay, so 2m divided by 2m, then I'm going to get minus zeta omega n plus or minus, so 2 and m is out, so I'm going to get omega n root of zeta squared minus 1, and that is it. In fact, 2m will cancel 2m. Therefore, so I can say that therefore lambda is what? Minus zeta omega n plus or minus omega n zeta squared minus 1. In fact, what this is saying is that Earlier on, what did I say? So earlier on, I said that x of t is what? A e lambda t. And interestingly, this is my lambda. Therefore, my lambda is actually so what this is trying to say is that my lambda that I want, or my s of t, is what? A1 e lambda 1 t plus A2 e lambda 2 t. All right. And what happens is that to determine the value of lambda, we are saying that lambda is minus zeta omega n plus or minus omega n zeta squared minus 1. Let's try to do something here. You know, we said that our zeta was what? C over C critical, which is the same as what? C over 2 root mk, which is also the same as what? C over 2 omega n times m. We said this was our damping ratio or damping rate. So our damping ratio or our damping rate. Now what happens is that if this damping ratio is equal to 1, then we have what we call a critically damped system. A critically damped system. And if our damping ratio is less than 1, then we have what we call an underdamped system. Our damping ratio is less than 1, we have an underdamped system. And then if our damping ratio is greater than 1, then we have an overdamped system. Overdamped system. All right. So I'm going to do separate videos for critically damped, overdamped, as critically damped, underdamped, and overdamped. But where we will start from is we are going to start or take off from this point. And I want you to appreciate this point very well, because that is where we are going to start all our analysis on. I hope the concept is clear. Thank you very much for watching this video.